talking to us about quasi-experimental causality in neuroscience and beyond, I would like to introduce Konrad Kording.
Wonderful. Thanks so much for having me. Let me start sharing my screen and hope that this will actually work out all right. Great. Here, let me pop out the Q&A so I can hopefully see it. It's a great honor for me to be back to NICO. It's been a while since I gave my last talk there. I miss you. I miss all of the guys that I know from back then greatly. And thanks for joining my talk. And with this, let's just start. So today we'll call about causal inference, in particular as it relates to neuroscience. And I believe that causality is a topic that all of us should think much, much more about because it's arguably central to pretty much everything that we want to do. And I hope I'll convince you of that. And I hope to give you a little bit of an overview of why causality is often so counterintuitive, and then talk a little bit about how neuroscience is done in neuroscience, how causality is done in neuroscience. And lastly, I want to tell you a little bit about quasi-experimental neuroscience, and you might care about it because the Nobel Prize in Economics was just given to Angrist and whatever the other guy is. In any case, to two people who worked on pretty much what I'll be talking about. So let's jump right into causal inference, or quasi-experimental causal inference, as we'll get to. So let's first start with the definition of causality. So people often talk about yeah, we can't agree on what we mean with causality. In reality, I argue we totally do. And this is the definition that I think if we all think hard about it, most of us are really willing to use. Let A and B be events, and there could be anything. Like it can be activity of something in your brain, of a cell maybe. It could be taxation rates, it could be how much a company makes, it could be if a person and me will become friends, or whatever it is. Let A and B be events, then causation exists if and only if we had changed A to A star, the probability of B would have been different. Now, let's be clear what that says. This doesn't mean that there's a direct link from A to B. It could be that A causes C, which then in turn causes B or something like that. In a way, this definition doesn't specify what comes in between. It just is a definition of the existence of a causal effect. And in a way that is lucky because the way physics works, you can say there's always things in between. There's no way how one thing ever directly causes another thing. So in that sense, it's a nice definition. I should also say, in the real world, in complex systems, we usually have systems that are reciprocally linked, where A influences B, influences C, influences A again, or something like that. This definition has no trouble with that at all. It just means that if I now take A at a given point of time, change it, it will change the future of that specific world. So that's the definition that I use. I will argue that most people who talk about causality use pretty much the same definition, but that's the precise definition that I use. Now, within neuroscience, what do people do about causality? So, or why do they want to do it? There's multiple fundamentally different reasons why people want that. The first one is I want to predict randomized perturbations. Why do I want to do that? I want to treat people. Like people, as neuroscientists, we're often interested in diseases. Say something causes something, or the drug, I want my drug to help a person, or I want an interaction between me and a person to make their life better. Or say, together with David Moore at Northwestern, we are looking for cases where maybe phones can have a causal influence on what people do. There's a lot of questions like that. So there you can say we can do an intervention. That intervention takes on the role of a randomized perturbation. We want to predict that. And in general, in neuroscience, we're often interested in that. The second reason why people want to do that is more a scientific reason for that, where what they want to say is, what does it mean for me to understand the brain? As an example of a complex system, and like that same problem exists in social systems that exists just about anywhere. When I say I understand how the brain works, for most neuroscientists, that means basically almost like understanding it like an electrical system, where it's one component affects another, makes Konrad do a bad joke. And this kind of causal way of thinking about things characterizes almost everything that happens in neuroscience. So if we want to put it into philosophical terms, what neuroscience strives for is a reductionist understanding of how the brain works. And for them, that basically means understand causality in the system and understand the components. So for a lot of people in neuroscience, when they use mechanism, they want something that also is causal, but that goes one step further, where I can say A makes B happen, but that transfer from A to B is underpinned by some physical system, C, that we can understand and study and so forth. So those are the reasons why neuroscientists want causality. Everyone wants causality. Now, and let me emphasize that here. In our life and in machine learning, everything that we do in a way has only one purpose, which is arguably make the world better for us, however we mean world better. And I'm not thinking in like a naive utilitarian, I just want everyone to be happy or something. But we all in our head have like a notion of where we want to bring the world to, and we want to make it better. And so even if we look at hardcore machine learning, the reason say why we do classification is because we can couple a process on it, and therefore classification makes that process better, and that process makes us money. So it's the causal link between prediction and causation that even justifies prediction. And ultimately the question in life is, would the world be better for me if I chose A over A star? So the choices that I make in my life can be viewed from a causal perspective. It doesn't matter if A or A star is correlated with good life. I want to choose A versus A star because it does make my life better. So it's ultimately a causal question, what we want to do in life. So what do we actually do? So there's different types of approaches that people take to get towards causality. There's some modern ones, there's some very old ones. So as one of the, and there's different logical approaches. So let's talk about the first one. This is the one that's logically most clean, which is the perturbations approach. Take a mouse. I want to know what the role is of some cells in the brain of the mouse. They develop these wonderful channels that basically let ions through when they're illuminated and don't let ions through if they're not illuminated. And thereby you can have mechanism where you can turn on or turn off a set of neurons and then see what happens in the brain. So you bring a virus into those cells, or like you have a transgenic animal, you bring in the light, and then you see, well, is the mouse still interested in water? Does the mouse turn right? Does the mouse remember something? There's a lot of those approaches. And then there's TMS. So basically I can produce a current in your brain. I put a big magnet over your head. I quickly turn it on, I quickly turn it off, induces a current, makes loss of nerve cells fire. And people use that, for example, as a treatment strategy. And then of course, there's the occasional case which get very famous, where someone got a steel bar right through their brain, and therefore there's significant parts of their brain missing. Now, what all these things have in common is that they can meaningfully be described as random. Not like the light you can turn on and off on a random schedule, as you can with the transcranial magnetic stimulation. And arguably, where in your head you get a projectile is also a random process. It's not perfectly random, but in good approximation. But what they also have in common, they're very low dimensional. So with the light, I can basically hit the brain with light or not hit the brain with light. It's one-dimensional. Same thing with TMS. Yes, I can zap at multiple places, but it takes me a really long time to get from one place to another place. Same thing with steel rods or like other damage, like stroke is another pseudo-random way of how the brain gets perturbed. So they're all low dimensional, they're expensive, and we are limited in what we can ethically do with those approaches. Then there's, of course, the approach of model comparison. So in model comparison, which is very, very popular in neuroscience, what people do is they build two models, A and B, nice models. And within a model, causality is always easy. Now, like I write down, take as input X, multiply it with alpha, now add Y to that, now spit that out as a result. So in that model, I know exactly how causality works. So what these model comparisons implicitly do is they implement two models and ask which model describes the data better. And when it comes to network inference, one of the famous frameworks for model comparison is Carl Freston's dynamic causal modeling. But they all suffer from the fact that they don't establish causality, they only establish model preference. So we don't know that the model maybe where A excites B is the right model. It could be that it's the other way around. We could never know. We just know that within that set of two trivialistic models that we compared, one of them is preferable to the other one. And there is nothing that says that if one is preferable for the other in a pairwise model comparison, that brings us closer to reality.
Excuse me, Konrad, we have a question here, if you don't mind. From Malcolm McIver, is understanding of a phenomenon exhausted by all causal knowledge of it? There's more. Knowing causality means you know how to intervene to change, but maybe there are aspects of a phenomena we want to understand that does not eventually result in being a knob we can turn on the phenomena. For example, knowledge about the history of our past, which may not admit of controlling since it is past.
Okay, I promised that I didn't seed that question, but it's a great question that I thought about an awful lot. I think that neuroscience throws away the baby with the bathwater by exclusively focusing on reductionist thinking. And I think that ultimately reductionist thinking can't deliver on the things that we really want from neuroscience. And here's why. So for a lot of phenomena, the kind of explanation that we might want to look for are of a different nature. And I want to, for people interested in the deeper philosophy, recommend a delightful book of Ernst Mayr about it, which is what makes biology unique, where you can say, let's say I observe that a bird has a beak. If I apply the standard causal reductionist thinking, the explanation of the beak is, okay, what's the beak? Well, the beak is made out of molecules that hold one another in place. And you can go all the way down to the atoms that ultimately make the beak. But if I ask you, why does the bird have a beak? The answer, because it's made out of molecules that stick to one another, is the most boring, stupid, meaningless explanation that we could think of. The right explanation for what we want of as an explanation as well. Turns out that there's like lots of bugs just like below the ground, and the beak is this magnificent tool with which like the bird can go in and get out the animal and take it out. So in a sense, this is an evolutionary, if you want, explanation of it. It's a backward-looking one, where it's like, what is the use that it has? And in evolved systems, we can meaningfully talk about use, because there's a niche, and we can talk about the niche. And so there is this history that we have going back. There's also, in a lot of cases, there's a learning history that we have for things. I should also mention that when it comes to neuroscience, the reductionist framework could be fundamentally frustrated. And there's a nice preprint that Tim Lillicrap wrote with me, where we argue that for complexity reasons, this can't work. So you can say, imagine I take everything that's in Konrad's brain and I elicit everything that Konrad knows that's really arbitrary in the world. Like, air balloons are red if they're in songs, like totally arbitrary. It could be a blue balloon, but happens to be red balloons. So there's lots of perfectly arbitrary information in my brain, and we can say there might be a certain maximal way how we can compress that. And now you can say, coming from there, the most compact description of brains can never be smaller than the amount of arbitrary information that we carry about the world, at least if we want to demand that the models actually work. So in that sense, this reductionist approach might lead us into a space in which there can never be a satisfactory answer that humans can actually understand, because our brain, as we learn, picks up information from a world that's around us that is remarkably complicated. But Malcolm, this is a wonderful question. We could spend any amount of time talking about it. But yes, what I'm talking about today is how to do causality if we want to do causality. I don't want to imply with that causality should be the route that we all take. I'm just observing the reality that neuroscientists really want that kind of explanation. So there's the other possibility, saturated structure equations and directed acyclical graphs. Again, full of prompts, namely what happens if we don't record all of them? What if we don't know the exact nonlinearities? We know how it fails in lots of cases, and it can't walk anywhere close to where we are at the moment. So now I want to give you an intuition of why causation is so difficult. So let's think about the trivialist little dynamical system. We set up this dynamical equation where we say xt plus 1 as sigma, where sigma is a nonlinear, could be a nonlinear equation. We will actually use the identity function here. So sigma doesn't even play a role, but we can build in a nonlinearity. It doesn't change much in the results you'll see. And then we have xt plus 1 is really axt plus epsilon t. So epsilon t is drawn from a Gaussian distribution. A is the matrix. So A here is the actual causal matrix. That's the matrix that characterizes how each component of X affects each of the other components of X at a later point of time. And we initialize it to 0. And now we need to make sure that everything is stable. So we set the largest singular value of A to be 0.99, just rescaling it to that. And now we have a system. And we might want to ask multiple questions for that, like how does correlation relate to causation? And also now what happens if we say only observe parts of it and things like that. Okay, so let's dive right in. So we can simulate that system, and importantly, we can change the dimensionality of it. So what happens if we have a small network, a small system? Do you think correlation and causation are the same, or do you think they're different? Okay, everyone make your opinion about it. I want to see if your intuitions are right about it. And of course I can't see you. So I just wanted you to ask you the question. So here's how that looks like. So what we do is on the top, we have the A matrix the way we generate it. Okay, it's nice and sparse and small. And then what we have at the bottom is the time delay 1 correlation matrix. And it intuitively makes a lot of sense. And like what we see here is if say neuron 1 is active at a given point of time, then neuron 0, which it's connected to, is going to often be active at the next point of time. And so what you see is here the correlation and causation are very similar to one another. So why on earth does Konrad have to give a whole talk on causation if correlation and causation are so similar to one another? Well, let's see. So it turns out that this is the kind of network that is like with 5 neurons. That's the kind of stuff that drives my own intuition. It's not like I can kind of simulate it in my head. And if not, I can like code up a little code that just does it easily. And I think a lot of us have done that and have thought about those systems. So yeah, correlation should be causation. What's the big deal about causation? Well, let's now do the same system, just make it big. No, just not 6 neurons like here, but 100 neurons. You see left here is the true connectivity matrix. On the right, you see the estimated connectivity matrix. And they're totally different. Oh my God, what's happening here? Why is it that in the small case, small networks of 5 neurons, the kind of stuff that I can wrap my head around, correlation and causation is the same. Now we have a big system, correlation and causation are very, very different. Well, the reason is if we have a big system, it has its own modes of activity that start being very strong. And if a system has its own mode, it means that it's no longer driven by the little amount of noise that every neuron is adding here, but it is driven by the dynamics of the system itself. And therefore correlation and causation are very, very different, because we should be thinking about in terms of the big components in which the network is naturally has dynamics that are naturally unfolding. And if we change the size of the network, what we have here on the y-axis is the similarity of A and R as a function of the network size, simply a correlation between these two vectorized matrices as a function of the number of neurons. And we can see that for that domain where we have these great intuitions of how things work, correlation and causation are very similar. But as soon as we go beyond that, and keep in mind, 100 is tiny relative to what's going on in the brain, the system is almost entirely driven by its own dynamics, and therefore it's very hard for us to use correlation to understand what's going on in the system. And I think I think from this intuition is where a lot of the bad treatment of it is driving. And let me read here, there's a question by Srinivas, who asked, isn't the effect because our intuition about causality is wrong? In bigger networks, causation is acting through loops with more edges. Yes, that is one way of saying it, but it doesn't make it more easy. You know, like the problem is that the loop doesn't go like cleanly through one loop. But yes, it's because of the existence of loops that the network has these own answers. Great, so that's the first one. So basically correlation is not causation. And I hope that I contributed a little to people's intuition about it. But here's the second one. Imagine in this case, we would record from all neurons, then the problem would go away. And like it's if I can do model fitting, let's say I have linear interactions between neurons and I fit all neurons, I can do multiple regression and the problems will go away. So the question here is like, will it save us that we have more than bivariate statistics? Now, it's not that I only have data from two things where I could calculate the correlation. I will in neuroscience maybe record from 100,000, maybe 10,000 neurons. So to which level will that help us? And for that, we can look for guidance to the econ literature. You can say, what is the brain? Now, the brain is a 10 to the 11 dimensional dynamical system. It's pretty big. What do we record about it? We record 100 or 1,000 dimensional projection of that system. And that means that there will be parts of the variables that we don't observe. So in the omitted variable bias equation, we say, well, the activities that we have, yi, is the sum of interactions with the variables that we did record from, the variables that we do have, xi beta, plus the variables z that we don't record that are still there, plus zi delta, plus ui, where ui is a noise that is independent, that is independent noise being added to every channel. So it's the same model, it's only acknowledging that we don't get at all dimensions. And even if we could record from all neurons, there's things happening within neurons. So it's not that a neuron, if I just know what the output is, then I have all the information. There's a lot of really complex things happening within neurons. Now, what happens from us not recording all neurons is that we will have a bias, and we can calculate that bias when we do a linear regression. And so what we have is we then have that the expected value for beta hat, our estimate, is the real causal interaction between variables, which is great, beta. And then there's a bias, and that bias doesn't go away in the limit of large amounts of data. Now, let's look at the bias. The bias has exactly the same form as what we do when we regularly do linear regression. It has x prime x to the -1, which is the inverse of the covariance of the autocorrelation, if you want, times the correlation here, the expected value x of x prime z. So that's how correlated these variables are. Now keep in mind that if you look at brain data, every variable is pretty much correlated with every other brain variable, like weakly sometimes, strongly sometimes. And I should say this, Coe and Kohn have a nice paper which says it's maybe in the range of 0.3 or something. But now keep in mind that per channel, what we should expect, therefore, is that the bias that every channel introduces is the same order of magnitude of the actual causal interactions between pairs of recorded neurons. But Now, let's think about this term. Like we have a 10 to the 11 dimensional model of which system of which we observe 100 or maybe 1,000 variables. But that still means that the number of unobserved variables is factor 10 to the 8 larger than the number of observed variables. So therefore, we should very strongly expect that the bias we introduce from having omitted variables is arbitrarily larger than the signal that we're actually looking for. So when we use these correlational techniques, and just to be clear, there's nothing that machine learning can do to make these things go away. There's a huge industry in neuroscience where people hope that if they do really complicated algorithms, these things will go away. If you formulate it in terms of omitted variables, there's nothing that makes these problems go away. Now, let me briefly, it's also a lot of people, when you then tell them that this is a problem, tell you, well, just get how many more subjects do we need to get? No, this is the bias in the limit of an infinite number of measured cases. So even if we could do fMRI scans on every human being alive, we will never make the omitted variable bias go away. Now, there's a question by Gerald Powell that I want to read, who asks, even in small networks, e.g. Lorentz logistic map, though many epoch causal variables are uncorrelated, although you only have 3 or 2 variables respectively. No. Yes, Gerald, I didn't want to say that small systems generally have easy causation. I was just making the point that large systems in lots of cases have very complex causality. Great question. Okay, now let's imagine that we're exceptionally lucky. Now, like we are talking about technical progress. So imagine we now go into that situation, like omitted variable bias, it happens because we don't record all variables. And in today's systems, we generally can't record all variables. But imagine we could. Would the causality problem then go away? And now I want to bore you a little bit with an estimation of the power that we'd have, because I think it's really insightful, and it suggests that even if we could record from the whole brain every neuron, every millisecond, that even then we couldn't get a causality. So let's see where that takes us. So we do linear, we assume that the whole brain is linear, which it's not, and that makes things much harder, but imagine it was. Okay, the whole brain is linear, and every neuron that's in the brain we're already recording. Wonderful. And we also know for each neuron, what are the presynaptic neurons. So we have connectomics figured out. A typical cortical neuron will have all their 7,000 inputs. And then what we look is, how well can we estimate that? And we can ask for linear regression, what is the variance of the estimator that we have? Beta is the real causal effect, beta hat is our estimate, and the norm between beta hat and beta, we can then estimate that it's going to be of the order of magnitude of the product of 2 terms. We have first the sigma p term. That's basically a term that will become bad if things are correlated. So let's ignore that term for the moment. And another term, square root of p over n, where p is the number of inputs that each unit has, and n is the number of points that we have, the numbers of samples that we have. So what we see here is that if it would take us a given number of examples to appropriately measure what's happening along one axis, we need p times as long to do it with all the inputs. Now, when it comes to neurons, and I want to estimate how strongly one neuron influences another neuron, I might want to run a 5-minute experiment on that to get a decent experiment of that, which means that if we have 7,000 of them, we need 5 minutes times 7,000, which starts to be a very long period of time, 35,000 minutes here. I don't know how many days that is. It's a bunch of days. Now, that is what we have for if the stimuli if the inputs are all uncorrelated with one another. But of course they're not. Like if they were all uncorrelated, then there would be nothing to learn about the brain. In reality, they're all correlated for the reasons that we discussed before. And so if we now want to get there, we have the sigma p factor. And I should say, here's a measurement. So in practice, we have an autocorrelation matrix, and it has some large singular values and it has some small singular values. Ultimately, we are solving an inverse problem. Like for the what we do is we do a matrix inversion somewhere. And what we have in the matrix inversion is we basically have a diagonal matrix where we have 1 over the relevant singular value on the diagonal, which means that the small dimensions are massively amplified, which means that noise that happens on the small dimensions gets to be really, really big. Which means that all of a sudden we need more and more data to get acceptable estimates of our weights. So roughly it's going to give us a factor that is proportional to the condition number that we have here, which is the ratio of the variance of the first to the variance of the last component that we care about. So this problem here might give us another factor of 10 to the 3 or something like that. Now, if we multiply the time that we have for one weight with the number of repetitions that we need here, it's going to give us an extremely long period of time. But now keep in mind that most neurons seem to change their properties maybe every 2 months or something like that. So this means by the time we would have measured what a neuron did, if we would record from all neurons, would probably take longer than the time it takes for a neuron actually to change. And so this means that even if we would live in this technical utopia where we could record absolutely anything, it might still be an unsolvable problem to get at the causal interactions between neurons. Now, we have a few more minutes, so let me briefly talk about quasi-experiments. So causality is hard. And in a lot of cases where we would like to have causality, we might be unable to get there. And I would say that the kind of problems that I spoke about, they also occur, say, in big data approaches towards understanding human interactions. So like, what if there are thousands of factors that somehow influence the way Konrad thinks about life? It means that then the problem that Facebook wants to solve to maximally make him vote for Republicans or something is equally forcing them into a very, very high dimensional causal inference problem, which might equally be unsolvable. And there's a lot of problems like that. So let's instead now look at a different domain, namely at a domain which usually is characterized by low dimensional problems. Now, like in economics, what the Nobel Prize was about was quasi-experiments. So quasi-experiments are cases, if you want experiments, what the economists call it experiments, are things where we randomize something. Observational studies are things where we just observe things and just try and make sense out of it. Quasi-experiments are cases where somehow the universe randomizes something for us. And for people who are interested in that, I can just mention this paper here, the paper with Leo and Anga. It has nice tutorials that allow people to play with it. Also at neuromatch.io, we have a nice day on the computation neuroscience course on causality with which you can play with these techniques. So, but let's talk about the logic. So I'm not promising you high dimensional ways of getting at causality. I believe they're fundamentally impossible. Okay, I've got to read Lewis's question just because it's fun. Lewis asks, if I can summarize your talk, the singularity is bullshit. Is this correct? My answer is definitely yes, but not only because causality in naive ways is impossible, but because of lots of other reasons. And we can talk about like that maybe in the final discussion, but like I think warnings about AI obsoleting humans were a little premature, but let's talk about that at the end. So let's talk about a case where we can get at causality. And this kind of causality, quasi-experimental causality, this is not like this tool that you can apply everywhere. Neuroscientists, of course, once they started reading about this, were like, wow, yeah, cool, now we solve all of brain science with it. No, we don't. But there's some cases where we can, and here's a case where we can. Famous paper here, a famous set of approaches. This is what's called regression discontinuity design. Imagine there's an exam. Every student takes that exam. And if you're above that score, let's say hypothetically it's 50, you get a certificate which officially says you're hereby declared awesome. And if you're below that, well, no certificate for you. And then you can look at So that's what we have up there. The probability of receiving that certificate is 1 if you're above 50, it's 0 if you're below 50. And now let's draw two hypothetical curves. Imagine we take like a random kid out of that group. And we just say, look, you get a certificate. I don't care if you actually did reach the score, like everyone gets a certificate. You get a certificate, you get a certificate. And then there's a hypothetical curve, like that kid who now goes to the world will maybe benefit from it. Maybe they'll be discriminated against for that. But you can say there's a hypothetical curve where it's a function of the exam score. I can plot their future achievement, and future achievement could be how much money they make, or if they get a stipend or something like that. And that's what we plot in green. They call it Y of 0, the economists. And we could run another hypothetical, which is no one gets it. Like you don't get one and you don't get one, like regardless of what you get. That's the red curve that we have. Now, in general, keep in mind, we observe the green curve only on the right side of the 50, and we observe the red curve only on the left side of the curve. So are we hopeless here? No, we're not. Why? Because I can guarantee you that these curves are smooth. Why can I be so confident about it? Well, if I take the same person and give them 5 tests in a row, sometimes they'll be above the threshold, sometimes they'll be below the threshold. There's a certain range in which that curve has to be smooth for that property. And that means that if we look just at the threshold, at that difference, this is a local causal estimate that is perfectly fine. And we know how to spot cheating in it, and there's a big literature dealing with it, and I don't have time to go through all that. Here's a famous paper that did that. They actually did that. There is a US national merit certificate. And there's 2 curves here. The age probability is getting a big stipend. Someone gives you a lot of money, and in the top curve is someone gives you any amount of money for studying later. And you can see that there's a clear discontinuity at that threshold, because it apparently helps to if it says National Merit Scholar in your CV somewhere. Having officially the statement that you're awesome helps, but keep in mind that it introduces an arbitrary nonlinearity here that seems a little questionable, maybe. So here's another paper that used that idea. It's a wonderful Angrist paper where the Jewish scholar Maimonides in the 12th century said, it's not right if a class has more than 40 students, and Israel, being very much convinced by the wisdom of Maimonides, basically said, sure, we're going to put that into laws. What that means is, if you look at schools that are just above 40, they must have 2 classes, and schools that are just below 40, they might just have 1 class. And so what he has here is the class size, and then from that you can say it's basically this random being above or below 40 that allows us to identify what the causal effect is of class sizes, and indeed class size has a big effect on student achievement. Now, there's sanity checks to make sure if there's cheating. I should also mention, if you use things like quasi-experiments, you will generally need more data than linear regression. We basically give away statistical power to have more causal validity. And that factor can easily go into the tens or maybe beyond that. So if you want to replace a randomized controlled trial with a regression discontinuity or any of the other quasi-experimental techniques, you will usually need much more data. At the same time, you don't need to randomize things. The people like the world randomizes them. And in that sense, you can have far larger numbers. I should also say this is an opportunity for neurons to learn, where you can say, if I'm a neuron, there's a threshold. If I get less than that current, I will not spike. If I get more than that current, I can spike. And you can build theories of how neurons learn, where it helps those neurons a lot and makes them unbiased if they basically learn from that mechanism. So that brings me to the take-home message. Causality is a central goal of neuroscience, and it's hard to obtain in practice, and our intuition really fool us when we think about causality. If we're intracellular, we can use spikes as learning signals, but there's always power as a major problem if we want to do causal inference. And I should also mention, we had that discussion with Malcolm earlier, maybe causality isn't even what we should want. And with that, thanks everyone for joining me in the talk.
Thank you, Konrad, for that fascinating overview of some of your research. We've got one question here. Oh, that was just a clap, clap. As we wait for some of the questions to come in, you're clearly so passionate about this topic, and we have many postdocs in our audience. I was wondering if you could talk to us a little bit about your career and how you landed to where you are right now.
Okay, so very happy to share that path. So I started out as a physicist, and ultimately, just a year and a half into studying physics, I felt that there was something missing for me. I loved physics, but it didn't seem to get towards the topics I found that I really wanted to ultimately work on. So I started working with the neuroscientists there. And the physicists made it clear that they wanted me to solve, to do physics. And I had a nice idea about using differential equations to describe how the early nervous system develops. And they were just, no, that's absolutely, that's not physics, despite the fact that it would have been the same mechanisms. So then I found at ETH Zurich, a professor who said, like, well, we think this is physics. And then I had to switch there. So since then, and maybe this is something that is important for postdocs to hear, since then, I've always been at that interface between different disciplines. It is a hard place to be. I managed to be relatively coherent in my first couple of years at Northwestern because, you know, that's what they want you to do. They want you to have like one niche where you're like the big guy. But interdisciplinary research, from my perspective, is where the really new things happen. And there's just so many biology experiments that do very similar things to other biology experiments. So it doesn't feel like that's a place where someone who really enjoys thinking will have a lot of fun. And so in that sense, I want to encourage people to seek these interdisciplinary spaces, but I want them to be aware that it's a harder path. And it's harder to get grants, and it's harder to get your papers into the top journals, because it's very easy to certify that someone is better than someone else. And it's like so easy. It's just like, oh, look, they do this. My stats is better. It requires like 2% less data. So let me publish, no problem. Whereas if someone says like, I think we're thinking wrongly about this, everyone has an incentive to not like it. And ultimately people do respond to incentives. So for people who are interested in this interdisciplinary space, and I'm sure a lot of people following this here are like by choice in that space, it is a harder path. And but it is, from my perspective, the most fun space. I think that's all that I can say about the path. Oh yeah, hold on. Let me share one more thing. Once I started as professor, they rejected my first 23 grants in a row.
Oh wow!
I would write grant rejection. I would always walk into the office of my chairman. There was Zev Reimer. Wonderful person. He would always sit there and give me some chocolate. He would always have some sweet stuff on his desk, and ultimately tell you, I'll be happy to look at your Ames page next time, but you'll be fine. And in the end, I get lots of grants later on in my life, but this difficult path happens early. Once people are tenured professor, it's great if you're interdisciplinary, because then people can work with you and you actually do invent interesting things, but it's much harder in that early parts of the career.
That's great advice, and I think you're speaking to an audience that's embracing that interdisciplinary aspect. I think you're looking here at the questions. We have a few of them coming in. Konrad, would you like me to start at the top, or would you like to dive in and take your preference?
Let me just start at the. Why don't you start reading them from the top?
Sure. I think. Oh, here we go. One from, I think Ching came in first. Ching Wang Any suggestions for doing causal inference based on observational neuroimaging data? We have so many open data sets. Thank you.
Yeah, Ching, I have like super bad news. I want to publicly declare here that I think that asking how causally one part of the brain affects another part of the brain is fundamentally impossible, which sounds insane if you think about it, because that's what 80% of fMRI research does at the moment. They use all these words, like they use the word functional connectivity, which assumes that it's functional and that it's connectivity, but really it's just a new word for the word correlation matrix. And they use words like Granger causality, which is really the benefit of predicting a signal based on adding one extra signal. So they're all correlational measures. They're all equally affected by the omitted variable bias equation. I don't think that causal inference on observational neuroimaging data is actually possible. The only causal inference you can make is from the outside. Not like I give you a stimulus and I don't give you a stimulus and I make this be random, which of them I give. That's totally causal. There's no problem about this. But if you want to know, does this part of the brain do something to this part of the brain? That's fundamentally impossible. And like, let me give you the thought experiment. You know, like we record a signal maybe of the order of how many brain areas there are. Let's say 100 of them. We have these 100 time series. It could be that we have these 100 brain areas that each interact with one another. Or alternatively, there could be a node somewhere in their little brain so that we never see it, of 100 neurons that interact with one another. And the whole outer part of the brain is just an amplifier of what these 100 cells on the inside do. In both cases, it would look exactly the same. And we could no way know that. And now, that's this one alternative, but effectively, because we have 10 to the 11 minus 100 unobserved dimensions, there's any number of dimensions in which this can happen. So that's why I hold that it's fundamentally impossible. And there's a paper that a manuscript that I co-wrote with, that's on bioRxiv, I believe, with David Mehler, which is called The Lure of False Causal Statements. So I do believe that that's fundamentally impossible. But great question. And it's not for lack of trying. Seriously, so many of my friends asked me how they could do that. I don't think it's possible. The best we can do is, of course, no, we can TMS them. Like if you want to know what does this part of the brain do, or we can inactivate it, just zap it. And then that part of my brain is basically depressed, and then we can see what's different. That's the only way that I know how we can get meaningful causality. And there's also all those problems with that. But wonderful question.
Thanks, Konrad. Maybe we'll go to one from Qinghua Li. Am I correct that your method focuses more on correlation? May I have you comment on other methods like Granger causality analysis?
Great question. Granger causality is entirely affected by the omitted variable bias problem and is not going to give you, and we should not expect that it gives at all meaningful causal estimates.
One from Malcolm again, very intrigued by your comments, Konrad. Have you extended the idea that this may be a theory for learning at the neural level to one at the organismal level? Do animals engage in quasi-experiments, and what would that look like to absorb causal structure? Looks like another good question.
Yes, so this is wonderful, and I think it characterizes lots of human ways of thinking. So if you want to learn, say, how causality works in some environment, and you have someone who's totally clueless versus someone who's like really, really good, you might want to look at the guy who's rather clueless, because they will try all kinds of things. And so they're basically doing randomized experimentation for you. Mm-hmm. Whereas the person who's like really, really good at it, they do all these complicated things and know things that you can't know. And you might want to not follow them. And so in that sense, I think that these ways of doing quasi-experiment-like reasoning really characterize the way humans think. But also, I mean, we bootstrap a lot of the things that we actually do by going and doing experiments. Now, like if you ever look at kids, they like go into a new place and like, let's switch this. So I think that it's not only that people learn over time to do quasi experiments or like to do quasi experimental thinking about the world. I think they also, no, it's also like if we almost made things, like we are mindful of that. We are mindful why we made the choices we made in the past, and we will learn very, very different from them given what happened. Yeah.
I'll go on. Thank you, Konrad. We've got 2 more questions we might be able to sneak in. Back again from Luis. Your points remind me of my favorite laws, the laws of thermodynamics and the limits they impose. Why do you think so many scientists want to believe that some new magical approach will make such limits obsolete? Meaning they believe in the singularity. They believe that machine learning AI can solve problems then when there is no information in your inputs.
Yeah, that's of course a very deep question. So let's talk a little bit about the state of the AI field. Now, like at one level, you can say AI is ridiculously amazing. Now, like it plays Go better than human beings, and it recognizes objects as good as I can, at least if these objects always appear in very simple situations. There's all kinds of things like how AI is amazing. But we need to reference the progress of AI against something else, which is at first, AI was trained on extremely small data sets. Say, think about 30, 40 years ago. So AI had much less data than any human being. And so, yeah, it wasn't so good. Now we are getting data saturated, which is basically we train our machine learning systems on every image ever uploaded on the internet, which is probably just about anything that's ever taken, and every text that has ever been part of the internet. So all of a sudden, basically, we train our models on everything. So much of that progress that we saw went along with just bigger data sets. And we know that in lots of these domains, the size of the data set is much more important than the rest. So we have these saturating things. The other thing is that there is this illusion in machine learning that we can have very compact learners. Well, as long as you give me exponentially more and more data, I don't need to build in much into my systems. But life is different. We are not preparing for redoing the things we did yesterday just a little bit better. What life is about, we're always preparing for the things that have never happened before. So our intelligence isn't like machine learning backwards facing, but all of biological intelligence is forward facing. We are figuring out what affordances are in various objects, not because it's helpful in the past. Now we know what worked in the past and what didn't work. Now we want to know these affordances before the problem even appears. So let's say if someone would put like a couple of lions randomly into Philadelphia, it would be a real sign of human intelligence that AI would never solve. Everyone would be like, yeah, let's just lock the door and we're safe here. It's kind of this thinking about like what would the world afford us to do if we are faced with things that we've never seen before. And in that sense, I think machine learning is a misleading story the way we tell that story to us. And arguably machine learning is a glorified lookup table in large parts of the system.
It's a glorified, sorry, Konrad, it's a glorified what?
Glorified lookup table. So there's so much text on the internet that most things you could possibly want to say, someone already said it. Right. And then it's easy because it's like all in that space. And I think I want to therefore be careful about this. And in general, this magical thinking, people always believe if there's something that they want, let's say the functional imaging literature wants causality. And therefore, they're willing to accept any algorithm as long as it's sufficiently complicated that they can't understand it, which promises to give them causality. And I think we have the same problem everywhere in precision medicine. No? There's if you read the literature, every day someone publishes this amazing magical breakthrough how machine learning will revolutionize healthcare. And well, it never happens. Why doesn't it happen? Because basically they've been believing in magic on the way there, and the algorithm isn't, because, well, magic is magic. It doesn't work so well here.
That may be one area where humans have the leg up, right? We can create and innovate, but not so with the algorithms. Luis had a follow-up question, and I do you have a hard stop, Konrad? Can you stay for just a few more moments?
I'll stay with you.
Okay, great. We'll finish Luis's question, and Takashi, I promise we'll get to yours. Luis commented, the reason why we do not remember with photographic precision, right? We learn approximations, which are more general and can handle new situations.
Yeah, no, the reason why we see isn't to store the pixels. It's because we're interested in a world behind the pixels, and we explain the world around us in terms of models, in terms of the kind of models that are good at the kinds of problems that we actually want to answer with them. And in that sense, of course, Luis, like we don't need pixel precise memory because it would be exactly useless. In fact, it's a total waste of memory, and so get rid of it as soon as you can.
It looks like people are really hanging on to your words here, Konrad. We have a few people leaving in spite of the 1 o'clock hour. The last question from Takashi, does the fact that neural interactions involve thresholding is important in figuring out causality from quasi-experiment? What if the coupling function is continuous?
Yeah, so according to our regression discontinuity quasi-experimental idea, neurons are effectively using their spiking threshold to figure out their causal effect. And let me briefly unpack causal effect. So in neural network learning, we do gradient descent. Gradients are the causal effect of a neuron in the linear approximation. So in that sense, neurons, as they do have a threshold, can basically see what happens when I just spike versus what happens if I almost spike. And by comparing them, they can observe their causal effect on like all the other neurons that they're connected to, but also the causal effect on, say, behavior or reward or something like that. And yes, it requires that there's this nonlinearity. Like there's 3 traditional quasi-experimental techniques, instrumental variables that can be used if there's a local source of noise in you, if you want. Regression discontinuity, which can be used if there's a threshold in it. And difference and differences, if we have 2 things that follow the same trend, but one of them gets perturbed at a given point of time, the other one doesn't. And so, yes, it requires those assumptions. And wonderful. Thanks, everyone, for all the great questions. It's great fun answering all of them.
Thank you so very much, Konrad. I'm sorry you can't see, but I'm sure everybody is giving a rounding applause. What a dynamic and interesting topic and presentation. Thank you so much for coming back to NICO. And in fact, we would love to see you back here in person when the opportunity presents itself.
Wonderful. Thanks for having me. Bye-bye.
Thank you so very much. Bye-bye, everyone. We'll see you in the winter quarter.